Our next speaker today is Amy Lovell from Michigan State University. She studies theoretical nuclear physics under Filomena Nunes. She's a third-year fellow and did her practicum at Los Alamos National Laboratory in 2017. And she'll be telling us about uncertainty quantification for reaction theory.
Thank you. Thank you. Okay, yeah, so I'll be talking about my work in quantifying uncertainties for reaction models. And there are many interesting properties that we want to understand about nuclei. These can include, how are nuclei shaped? Are they spherical or deformed? And if they're deformed, what kind of deformations do they have? How does the structure of nuclei change as we move away from the valley of stability? And I guess in this, I've sort of committed the cardinal sin of nuclear physics where I'm not showing you a chart of the nuclei, so I can point to the valley of stability and move away. But we want to answer questions about, do the structure change and how do our models have to change as we go and create, heavier nuclei, more neutron-rich or more proton-rich nuclei? And then what are the internal configurations of nuclei? If we can't just describe a nucleus as a spherical blob of neutrons and protons, do we have any valence nucleons? And if so, where are they located with respect to a more central core? And all of these questions can be probed using reactions, and therefore reaction theory as well. So there's several different kinds of reactions that can be used as probes, and I'm just going to give a couple of examples here, and this is not inclusive. But we can use reactions such as elastic scattering, where you have a projectile incident on a target at some energy, and you get the same thing out at the same energy, shown here experimental points in black, compared to a reaction calculation for a differential cross-section. And this can give us information about the strength of the interaction between the projectile and target, as well as the geometry of the interaction. Likewise, if we consider inelastic scattering, here shown in the green and blue, where you have the same process, just a different energy in the outgoing channel, we can answer questions such as, what are the shapes of nuclei? What are their energy levels? If we instead look at something like a single nucleon transfer, where maybe you'll have a deuteron, a proton and a neutron impinging on a heavy target, it transfers either the neutron or the proton into some state, and then the other particle is outgoing. We can look at the levels in the target nucleus, what type of angular momentum is transferred and how much. And this can be seen in different shapes of the differential cross-sections as you've transferred a different amount of angular momentum. And so to get all this information out of experiments, you need a well-defined reaction theory, which is where we come in. And so the thing is, we make a lot of approximations when we do our reaction theories, and these introduce uncertainties into our calculation, which can broadly be described in two types. Systematic uncertainties, which come from sort of the shape of the model that you're using or the shape of the interaction. Have you used a Wood-Saxon potential, or are you using a Gaussian? Simplifications that come into your model. My group at MSU treats few body problems, so instead of solving the whole A+1 body system, if you have your target, your A body target, and your one body projectile, we simplify this into a 2 or 3 body problem, so that's more tractable. We also have statistical uncertainties that come from constraints on parameters, from fitting to data, or sort of the size of the model space that you're using. And although all of these are important to form a full picture of the uncertainties that are present when we do calculations, what I'm going to be focusing on is really these parametric uncertainties. So the types of reactions that I'm interested in are single nucleon transfer reactions. So again, we have a deuteron impinging on some sort of heavy target. It leaves behind the proton or neutron in a bound state with the target, and then the remaining neutron or proton flies away. And we want to calculate the cross-section of this reaction, which takes into account the wave functions of both the initial system and the final system, for which we need interactions between our projectile and targets. These interactions are described in terms of a phenomenological optical potential, which has both real and imaginary parts. The imaginary part takes into account the loss of flux to channels that aren't explicitly described in your model. We have both volume terms, surface and spin orbit terms, and also Coulomb terms, when we have two charged bodies, which are described as either a Wood-Saxon or a derivative of a Wood-Saxon, the sort of shapes that you see here, where you have sort of a deep volume term, a peak surface term, and then a long-range Coulomb. So each of these terms can be parameterized by a depth, a radius, and diffuseness. So then when we're looking at our overall potential model for a target and a projectile, we have somewhere between 6 and 12 free parameters, depending on which of these terms are included in our model and which are important at different energies and for different projectile target combinations. And so this introduces uncertainty because these potentials are typically fit to data. And so for a given parameterization, depths, radius, and diffusenesses, they're typically formed in terms of an energy dependence, a mass dependence, and maybe a difference and asymmetry dependence, which is just the difference between the number of neutrons and protons. And so these forms will be fit to different types of data, such as elastic scattering data, reaction cross-sections, polarizations, and depending on the different sets of nuclei that are included in this fitting, we typically would fit across various masses, various energies, so that you form a global parameterization. But the choices, and even the choices of this form, can lead to uncertainties within your model. And I'm going to illustrate this by using a very exotic example. This is tin 132, which is very, very neutron rich. It's, don't have a lot of data, so it's not an ideal example, but as we go to facilities such as FRIB, which is being built at MSU, this is a very important part of the nuclear chart, and we need to understand how our models and how physics works out here. So in this case, this is the experimental elastic cross-section for this tin 132 deuteron elastic scattering at 10 MeV. We have 4 different potentials that I've calculated or done a fit to. These first 2 in blue and green are these global parameterizations that I was just talking to. They were fit to a large source of data. And you see, in the region of the data, they describe the data very well. But we can also start from these and do a local fit to this data, which also fits the data very well. I have the chi-square per degree of freedom for each of these fits here. They're very similar. But outside of the range of data, we have wild oscillations and just very different results from these 4 parameterizations. And so we really want to quantify the uncertainties that are coming from these different fits. Because then if we consider taking these parameterizations and making a prediction for now the single neutron transfer on this nucleus, again, we see wild differences between these 4 calculations where the parameterizations are fairly similar. And not only are they very different from one another, but they don't describe the data either. And so work has been done, or typically what's done in our field is that people will take 2 parameterizations, do a calculation, and say, okay, my results are different by 10%, so there must be a 10% uncertainty. But the goal of this project is really to systematically quantify the uncertainties and coming from a single parameterization and not a comparative way. So there are many ways that we can do this, but we chose to work with Bayes' theorem, which is shown here. And the goal of this is to really calculate the posterior distribution, which in our case is the probability that the parameters that you've gotten from fitting are correct after you've seen the data. What goes into this is a prior, and that's what's known about your parameters before you know anything about the data, a likelihood, which contains your chi-square function, and then this Bayesian evidence, which essentially, or practically, is you sum up all of your different prior and likelihood combinations over all of your different parameterizations, over all of your different models, etc. And so, in principle, if you could calculate all of these parts, you would be able to exactly calculate your posterior. But the evidence is very difficult or often impossible to calculate numerically, and so we use Monte Carlo methods to sample from our posterior distribution. And the way this works is we start with an initial parameterization, we calculate our prior and our likelihood for that parameterization given a set of data. We then pick a new set of parameters out of a normal distribution and calculate the prior and the posterior, or the prior and the likelihood using our new set of parameters, and then compare the two. And if this ratio is greater than a random number between 0 and 1, we accept our new parameter set, and we start the process all over again. If this condition is not fulfilled, we throw out the new parameter set, and then start again from our initial parameter set, pick a new one. And we go through this process until a specific predefined number of parameter sets have been accepted by this condition. And so practically, when we do these calculations, there are several potentials that we're interested in. We need to know the binding potential between the neutron and the proton in the deuteron. For the specific reaction theory that I'm not going to go into, but that I am discussing, this adiabatic wave approximation, we constrain our deuteron-target interaction by through nucleon-target interactions. So we need to know the proton-target and the neutron-target interactions. And this is for our incoming channel. Then for our outgoing channel, where we have this A+1 system, and the outgoing, I'll talk about protons, because I'm talking about single-nucleon or neutron interactions, but we need to know the bound state between our transferred neutron and the target, as well as the scattering state between this outgoing proton and our A+1 body system. And in this work, I only focused on the uncertainties from these scattering states, so these three in black, and we fixed the interactions between the bound states. Obviously, eventually this should be taken into account, but these bound states are typically better known than the scattering states. And so there are three interactions that we have to constrain. And the first one that I'm going to talk about and show in detail is this calcium-48 neutron interaction. So ultimately, the reaction I'm talking about is calcium-48 DP. So here I'm showing the posterior distributions. So we fit to neutron elastic scattering data, and from this extracted our parameters for the volume, real and imaginary terms, and their surface terms for the depths, the radii, and the diffusenesses. And again, the histograms are our posterior distributions compared to these gray lines, if they show up, are our prior distributions. So the one thing we notice right away is that our data has significantly constrained these parameters. Right? Our priors are very wide, and the posteriors are significantly narrower. And then also, we can see that all of these parameters are physically reasonable. And I've given the means and the widths here since the scales are a little small. So then we can take these posterior distributions and calculate an elastic scattering cross-section for each set. And that's shown here. These bands defined 95% confidence intervals. So now we've put confidence intervals on an elastic scattering calculation, which has been constrained by this data shown here. And so we get a good description of the data, and we have reasonable uncertainty bands as well. And then so if I showed you this ad nauseum for the other two reactions that I cared about to constrain the transfer cross-section, you'd see that we also have the incoming proton channel and the outgoing proton channel, which all three of these combined will make up our transfer cross-section. And in all three cases, you see that we do a good job describing the experimental data, and we have fairly well-constrained bands. So then these three posterior distributions can be used to predict a confidence band for the transfer reaction that we're interested in. And that's shown here. So again, this is the transfer cross-section for calcium-48 DP at 24 MeV, and compared to data at about 20 MeV. And so you see that, again, do a fairly good job describing the data, and again, we've predicted confidence bands for this reaction. We can then also define sort of our experiment or our theoretical uncertainty which we take to be the width of the confidence band divided by the mean value, which is what's plotted over here. So you see we have an oscillating uncertainty, but at the peak of the cross-section, which is where we can extract a lot of information, we have about a 35% uncertainty. And typically the uncertainties that people assume come from these parameterizations are somewhere between 10 and 30%. So we're around there, a little high. And then the question we can ask is, well, if we want to reduce our theoretical uncertainty, which I think we always do, we get to the 10% or less range, how can we do that? So one of the questions we can ask is if the experimentalists can better measure their data, will this help us? And so that's what I'm showing here. Here I've artificially reduced the experimental error by half. So I assumed before that there were 10% errors on the data. Now there's 5% errors on the data, and what does that do to my distributions? And so we see that in many cases, so the gray is what I showed you before, we have about the same mean values for our distribution, but we do have somewhat narrower posterior distributions, although not in all cases, as you can see for some of these parameters. If we then use this to calculate our elastic scattering cross-section, if you can, may not have been the best color choices, but you can see that there is some narrowing of our elastic scattering. And then if we use this to, again, make our predictions for transfer, we see that there is some narrowing of our confidence intervals, but it's a narrowing of about 30%. So we've halved the experimental uncertainty, and we only have a 30% reduction of our theoretical uncertainty. So this clearly is not the entire answer. And so then the other thing we can do within this framework is that we can make direct comparisons between different physics models. And so in the previous model I talked about, we constrained our deuteron interactions using nucleon-target interactions. But if we sort of go a level up coarser, we can talk about the distorted wave-borne approximation, in which you constrain your deuteron-target interaction by just using the deuteron and the target. And so you fit to deuteron-target elastic scattering data, and the outgoing channel is exactly the same. So we can do this, again, using 10% and 5% experimental errors. These are deuteron target elastic scattering, and again, describe the data well. We see there's not as much decrease as we decrease the experimental errors. So then we can finally compare all four of these predictions, the two adiabatic calculations at 10%, 5% uncertainty compared to the two distorted wave calculations. And at forward angles, these calculations are very different and the uncertainties are different, but at the point where we have experimental data to compare to, we can't distinguish between these four models. And we can see that if we, again, look at the percent uncertainty at the peak between these four models, okay, the adiabatic formulation does have a smaller uncertainty than the distorted wave, but when you're extracting the physics, you can't tell the difference between these four calculations within these uncertainties because they're so large. And we're able to do this for a variety of reactions. This is just sort of a summary of the work that I did. And if really what we want to focus on is this epsilon 95, which is the 95% confidence bands at the peak of the transfer reaction, the uncertainties. And we see they can range anywhere from about 25% to 125% uncertainty, which in general is significantly larger than the 10 to 30% uncertainty that people have assumed come from these parameterizations. And so this is something we really, really need to focus on if we want to even then tackle model uncertainties, because that'll just grow these uncertainties. And so, in conclusion, we've used Bayesian methods to calculate confidence bands on both fitted elastic scattering and predicted transfer calculations, and the uncertainties we find can be significantly larger than what people have previously assumed. But we can start to answer a lot of exciting questions within these Bayesian methods, such as, how do we reduce our uncertainties? Is having better measured data the answer? What can we look at between different models? And can we really tell the difference in our models? And although this is really exciting, what I think is particularly exciting is all of the future work that can be done within this, and work that my group is continuing to work on. And so we're working on reducing our parametric uncertainties, maybe by fitting other types of data, which they've done for these global parameterizations. We will eventually be able to take model uncertainties into account, and particularly through this Bayesian framework. And then this will be useful to define the full uncertainty, what's really coming from these few body simplifications that we're making. And then also, as I briefly mentioned, there are a variety of ways to define uncertainties, and we're really interested in looking at comparing Bayesian to other maybe chi-square minimization techniques that have historically been used, and seeing sort of the practical differences between these two. And so then I would just like to ultimately thank my group, and especially thank this program, Krell and NNSA, for allowing me to do this work and then pushing me into the postdoc position I just got. And I'd be happy to take any questions.